Welcome! This video is an introduction to the oscillator circuit, which is an important building block in many modern electronic devices. The goal of this video is to give you a quick 5 to 10 minute overview of what an oscillator is, how it works, and how to build one. So let's go ahead and get started. Most of the important electronic devices in your life, like your phone and your laptop, depend on circuits to run. For example, if we look inside any of these devices, we'll probably find a digital processor that connects to some other circuits that allow for wireless connectivity, such as Wi-Fi or Bluetooth. We'll also find a memory that holds things like your data and your files, and also some sensors that measure things like temperature or maybe even your heart rate. The thing is that all of these circuits need something that tells them when to run. Just like a team of rowers has somebody sit at the front of the boat to tell them when to row, or like an engine has a control unit that tells the spark plugs when to fire. For circuits, this is the job of the oscillator, which is also sometimes referred to as a clock source or just a clock. The oscillator produces a voltage that varies across time. That voltage can take on one of two values, either a high voltage or a low voltage. This voltage is then sent to the circuit, and there's various ways the circuit can interpret this voltage, but typically it looks for the point when the voltage transitions from low to high. This is referred to as clocking on the positive edge. So, each time this positive transition occurs, the circuit interprets that as its signal to go. At each go signal, the circuit does a small amount of work. Maybe it will add two numbers together, it might move some data from one place to another, or it'll send a small amount of data wirelessly. So now we can go a little bit further in depth with this voltage waveform and figure out how to characterize it. The most important characteristic is the timing, so to help quantify that we can define the amount of time between two consecutive positive edges as the period, represented by a capital T. The period is the inverse of their frequency, so if you've ever heard of a 3.4 GHz processor, or maybe a 102.5 MHz radio station, those numbers are both referring to frequencies, so you can use the above equation to translate between the frequency and the period. In some cases, the positive edges might not come at a fixed rate. This means that the frequency of the waveform is actually changing across time. So now that we understand the frequency of the oscillator, how do we determine the other performance factors and metrics that we care about? In general, the oscillator frequency should be predictable and reliable, just like the engine and the rowboat examples. First and foremost, we care about the frequency of the oscillator. What frequency does it run at, and how precise is that frequency? Does the oscillator have any tuning or trimming ability that allows us to change the frequency? How stable or robust is the frequency? Will it maintain the same frequency across all of time, or will it vary? One of the factors that affects stability is temperature. Ideally, the frequency is constant across all of temperature, but in reality, the oscillator frequency will vary a little bit. Sometimes it might rise, or sometimes it might decrease. Another factor that affects the stability is supply voltage, which can influence the frequency the same way that temperature can. Finally, we have jitter or noise. This refers to very small fluctuations in the frequency across time. One of the last metrics that we care about is the power of the oscillator. This refers to how efficiently the oscillator can do all of the above items. So let's go over a conceptual example of an oscillator. Say we have the following setup. A faucet is located directly over top of a bucket that has a drain at the bottom. At the edge of the bucket, we put a lever and tie a small weight to it. At the same end of the lever, we also tie a string to the drain of the bucket. Now we turn the water on, and the bucket begins to fill up. Once the water is at the top of the bucket, it begins to overflow. This pushes the lever down, which then releases the drain of the bucket, draining all the water. However, once the bucket is drained, there's no water overflowing and holding the lever down anymore, so it returns back to its original position. As it does this, it pulls the drain closed and the bucket begins to fill back up with water. We can see how this functions as an oscillator by paying attention to the vertical position of the end of the lever as the bucket goes through its cycles of filling and then draining. You'll notice that the waveform that's generated here has the same characteristic as the other clock waveforms we've seen previously. So now let's try to relate the performance of this conceptual oscillator with the points that we talked about previously. First, the frequency itself is set by the speed of the water coming out of the faucet, as well as the size of the bucket. The trimming and stability of this oscillator are based on the above parameters. So for example, if the speed of the water coming out of the faucet is changing, then the frequency of the oscillator will change as well. We can think of the power as the amount of water that gets used in order to make the system oscillate. If the amount of water coming out of the faucet is small, and the bucket itself is very small, then it shouldn't take very much water to get the end of the lever to oscillate. So let's take this conceptual oscillator and turn it into a real one using circuits. Let's take a current reference called Iref and connect it to the top of a capacitor called C. The voltage at the top of this capacitor is called Vcap. We'll connect it to a circuit called a comparator. The other input to the comparator will be a reference voltage called Vref. The output of the comparator, Vout, will change its value based on the two inputs, Vcap and Vref. In this instance, Vout will be high if Vcap is higher than Vref. If Vcap is lower than Vref, then Vout will be low. We'll add a switch onto the Vcap node that connects the top of the capacitor with ground, and then we'll take the output voltage of the comparator and use that to control the switch. To relate this oscillator with the previous conceptual oscillator, we can say that the Iref represents the faucet, the capacitor represents the bucket, the comparator represents the lever, and that switch on the far left represents the drain. Now, let's look at the voltage that this circuit produces over time. First, let's just assume Vref is some arbitrary value, and it stays constant across time. We'll assume that the voltage of Vcap and Vout are both zero. The reference current flows onto the capacitor, charging its voltage up. This means that Vcap will start to increase. Eventually, Vcap crosses Vref, and the comparator recognizes this and transitions its output voltage high. When the comparator output voltage goes high, it turns on the switch, which connects Vcap to ground, which is 0 volts, so now Vcap will discharge. Shortly afterwards, the comparator recognizes that Vcap is now less than Vref and it transitions its output low. And that completes one cycle of the oscillator. This operation will continue as time goes on. The output of the oscillator, which is the output of the comparator, creates a periodic spiking characteristic similar to the ones we've seen previously. Even though this isn't as clean and perfect as the previous waveforms, there are some simple circuits we can add on to the end of this to clean that up. Also, just like the conceptual oscillator that we already looked at, this real oscillator depends on the same factors for its performance, such as the speed of the reference current, the size of the bucket or the capacitor, and the characteristics of the comparator. This plays a big role in how quickly the capacitor is discharged. Because the process of discharging contributes a small amount of time to the overall oscillator period, it still plays a critical role in determining the frequency. So, components like the reference current and the comparator need to be designed very carefully to ensure that they operate as expected and don't degrade the stability of the oscillator. Even after dozens of years, circuit design engineers are still coming up with new ways to design oscillators, so that they have higher stability or they're more power efficient. And that concludes this introduction video. Hopefully you found it interesting and learned something from it, and thanks for watching.